then one component for the OR, and similarly if other components required for AND or whatever the small module required, we can write. Main motive for this, main advantage for using these component is we can declare component only once and we can recall as many times as we required. Means we in the combination data flow or behavioral, we have to specify each and every step, but in the structural we need not to follow our truth table. We write the components, and then if same component is required 4 times 10 times, we need not to write again and again, we can recall for 4 times 10 times whatever time we require. Another major difference here is we have to define this port mapping. Port map is nothing but it's just a interface of interconnects with the different module. As we are seeing, we have module for the half adder, we have module for the OR gate, AND gate, XOR, or we have to interconnect these separate modules with the help of these signals that we have declared here, S1, C1, C2. Signals are nothing but the interface, and that interface we are doing here with the help of port mapping. What is port mapping? Port mapping is port we defined in the start, that is our input and output, and map is interface, and with the half this is half adder 1, half adder 2, OR and AND behavior. And in this structural type of modeling, the main things are components, signals and port map. If these three are correct, then you can say our if these three are cleared how to define, then our structural modeling is very easy as compared to behavioral and data flow. Next, after simulating the structural type of behavioral code, we will come to this type of basic circuits of full adder and waveform of the simulator to verify our basic function. Next is the multiplexers, another type of combinational circuit, that is special type of combinational circuit. And in this what we have a multiple inputs but only one output, and these inputs depends upon these select inputs, select lines. If we have basically the relation is inputs n is equal to 2 raised power s, s is the our select line. If we have 2 select lines, then our inputs D0 to that will be up to D3, means we have 4 inputs. If we have here as select lines 3 select lines, then accordingly our inputs will change. This is another pin E, that is the enable input, and this is basically required for cascading. If we have 2 or more number of multiplexer we have to connect in the cascade, then we have to connect this enable signal, and this is basically a active low signal. Then these are the different type of various versions of the multiplexers, that is 2:1, 4:1, 16:1, 20, 32:1, and that is basically differentiated based on our select lines. Next is the 2:1 multiplexer. Here we have one select line, 2 inputs, that is W1, W0 and 1 output. Accordingly we have the truth table. And no, if we have to implement our this multiplexer with the help of VHDL, what we have to do? We have to implement this truth table. Next, VHDL code for 2:1 multiplexer. Here same thing, we are defining library entities. In entities our inputs, that is W and 1, you can see here these are the inputs, and output is 1, that is F. Here we are defining 1 output, and AND mux 2 to 1. Next is the architectural flow, is main for the functionality, and if your sorry, when S is 0, then your F will be W, and you can see here if S is 0, our function output that will be W0, and if S is 1, your F function will be W1. Same thing we are implementing it with the VHDL. Next is cascade of 2 multiplexer. We have 2 input, one multiplexer, one second multiplexer, and output function will depend upon if our select line, this select line is high, then our output function will be having W1. If our select line 2 is high, that is 1, then our output function here we will be having W2, else W3 will be available at the out. Same thing we will implement with the behavioral code. Here come to the main architectural body, same thing as per this table we are implementing with the code. Next is the 4 to 1 multiplexer. Into 4 to 1 multiplexer mean we have 4 inputs, 1 output with 2 select lines, and accordingly we have 2 table here, and this 2 table we have to implement with the help of VHDL. Here again same thing, 0 0, when 0 0 f output function will be W0, when 0 1 then W1, and similarly other functions. Next is the encoder. In the encoder type of combinational circuit, we have n input lines, m output lines, and encoder is basically required for different type of functions like your priority encoder. We have to define which input should be available at the output according to their priority. If we have for example we have decimal to binary converter, we have 10 input switch from D0 to D9, and from all these 10 switches mean their function is either 0 or 1, either on or off, and if that switch is on mean that is high 1, then that will be available at the output. If 2 or more switches are on at the same time, then our this priority encoder will identify which out of those 3 which should be available at the output. And same thing you can see with the help of this block diagram, priority encoder. Here we have D0 to D3, these are the 4 inputs and 2 outputs, and this D0 have the lowest priority input and D3 have the highest priority input. So if at a same time our D2 and D3 are activated, means high, then our this priority encoder what will do, D3 will be available at the output instead of our D2 because this one having a higher priority. Accordingly our output function y0 y1 will be activated, y1 or this 1 1. Then this is a truth table for the priority encoder, 4 input 2 outputs with 1 enable, and when our z is high, enable is high, then our these function will be implemented as per these inputs, and whatever these are the 4 switches, and you can see from the this table only one W from W0 to W3 will be high in the different states, and whatever the input is high, accordingly our output will be available. And same thing we have to implement with the help of VHDL coding. Now VHDL code for the priority encoder, same thing we are writing our entity architecture. We have to see, we have to implement when W3 is 1, then our 1 1 will be available in the Y output. You can see here when we have 1 1, this 1 1, if this our W3 will be available in the output. Similarly if we have 1 0 W2 here and 1 0. Similarly according to our truth table we have to write our architectural body, and we have to simulate and write the find out the function of encoder. Next is the decoder. Decoder is again a combinational circuit, that is you can say reciprocal or to encoder, and that is very similar to identical to the demultiplexer without any input data. So in decoder we have n inputs line, m outputs line, and here output lines will depend upon m will be is equal to 2 raised to power n. If we have n 2, then output lines will be 4. Accordingly, again with the increasing of n, our output will be increasing. Similarly, very similar function of the demultiplexer. And the application of this decoder is code conversion, VCD to 7 segment decoder, and some other applications. And same thing, we can have a 2 to 4 decoder. This is the truth table for our 2 to 4 decoder, and this is the graphically symbol, and this table again we can implement with the help of behavioral coding. This is a behavioral code for 2 to 4 decoder, and again you can see our main body, that is our architectural body according to the truth table, and we are writing, we can simulate and find out its functionality with the help of tool. Next is the 4-bit number comparator. Comparator is a combinational circuit that compare two numbers, that is A and B. A number may be 4-bit, 8-bit, 16-bit, or B again can be 4-bit, 16-bit, or higher number, and we have to compare these number. Means either these two number are A and B are equal, then this will be activated. If A is greater than B, then this output will be activated. If A is less than B, then this output will be activated. This is the main function of our comparator, and same thing we will implement with the help of BHDL. Here one other thing to note, here we are declaring a library that is unsigned for number, and for unsigned mean our comparator will compare the number those are positive. Okay, and we are writing here same thing as per our previous behavior, that is if this A and B, if they are equal, then this one high will be available with the A equal B output. Then if A is greater, then this output will be activated, that is A greater than B, and if less, then that will be activated similarly. Next is the behavioral code for 4-bit signed number comparator. Here in the previous we are declaring here library unsigned. Now we have to writing code for signed number, so we have to declare the library of signed number, and again similarly declare the entities and write our main architectural body as per the function of comparator. Now next is the synthesis, BHDL synthesis. Till now what we discussed the basics of BHDL, then their implementation for combinational circuits, that is our adder, decoder, encoder, comparator for with the help of BHDL. Now our BHDL code is ready, we simulated, we get the output waveform, and we verified our function, that is functionality of our combination circuits is okay. Now further step is how to implement, how to synthesize this code on the hardware, and that is the part of synthesis. Synthesis is a process of generating the circuit gate level implementation from BHDL code, and this process, synthesis process, basically will be useful for those students those would like to work for their minor projects or major projects based on the BHDL. If based on BHDL means once our code is ready, we have to verify and implement on the hardware with the synthesis process. And synthesis process are basically two types. One is the behavioral synthesis and other is RTL synthesis. Our behavioral synthesis, as it's clear from its name, will check its functionality, behavioral and final implementation according to its operation schedule, resource building, control generation, etc. And in RTL synthesis, what is basically, that is interfacing and optimization. Interfacing mean we, as we are discussing in the structural modeling, we have different components, and we have to interface with the help of RTL synthesis, and then their operator, storage, interfacing, mapping and interfaces. This is the behavioral and synthesis. This code of combinational circuit that may be with the help of our data flow, behavioral and structural modeling. Any type of modeling code may be there, and in synthesis process what we have to do, we have to transfer this behavioral code, transfer at the gate level, and then gate level we have to optimize. First let us see in the code which type is will be preferable for our design. Mean either behavioral is preferred or structural is preferred. Behavioral, as we are saying, we are using the process statement, and that is sequential and in simulation. So that may not be useful for the high speed application, because in the behavioral we are using the sequential statements. So for high speed of application we have to go for the structural type of modeling, but at the cost of power. In the behavioral type, power consumption and power dissipation will be less as compared to the structural. In structural modeling what will happen, our processing is parallel, so speed is very high, but due to large number of components, due to signal, due to port mapping, our power consumption will be high. So we have, there is trade off in speed and power, and that is applicable in the behavioral and structural too. So before go to the synthesize process, here we have to first check which type of modeling will be suitable for our design, and once our design is ready with the some specified behavioral modeling, then we will transfer at the gate level, and then we will go for the optimization. Now the thing is how to optimize our design. Optimization means, for example, if we take a simple example of arithmetic circuit xk plus bx. If we take a simple example of xk plus bx plus c, and if we take x common here, what will be here? X plus b, and that will be plus c. Same function is there here. What we require? We require 1 multiplier and 2 adder, mean 2 multiplier and 2 adder required to implement this function. If we take x common, what will be required here? We require 1 multiplier and 2 adder. So means we optimize our simple expression from hardware point of view. Previously we required 2 multiplier, 2 adder, now we require 1 multiplier and 2 adder. This is a simple example for the optimization. Same thing we are doing here, mean we have, during optimization our main function, main functionality, that should not alter, that should be changed as required, but the hardware requirement, resources requirement, that should be minimum. So in the optimization we have to minimize the hardware, that will be having two positive point. One is minimum hardware requirement, means minimum area for our design. Second is minimum interconnects required for the different modules. Minimum interconnects mean minimum delay is there, so high speed will be there. So next is the BSDL modeling and synthesis. In the start we are saying we have to think about the hardware, what we are going to design, and with the help of modeling, that modeling, three type of modeling we discussed, and with the hardware that we have with the modeling we have to convert with the into the BSDL description. And once our BSDL description is ready, then that BSDL description with the help of synthesis, again we have to transfer to the hardware, and that is the main function of our synthesis. Next is the BSDL description space, that is they are both are interlinked, BSDL for synthesis and BSDL for simulations, and we have to first go for the simulations and then go for the synthesis. This is the methodology for the combinational circuit design. as in the start we started with our requirement, that is our requirement in the combination circuit may be requirement according to our adder, how many inputs are there, that is the adder is 4 bit, 16 bit or 32 bit, or maybe for multiplexer maybe how many number of inputs are there, output is 1, for demultiplexer, for encoder, decoder, whatever the combination circuit we are going to design, our specification requirement we have to define in the entity in the start. Then we have to go for the RTL model, that is our BHDL type of modeling, and then we have to go for the simulation. And simulation means here we are doing the simulation for its checking its functionality, and test bench will be required at the each stage, and this test bench is at this first stage we required for the calculating its functionality, mean our input number of combinations are okay as per our requirement or not. If that is okay, then we have to go for the other step, that is synthesis. Our code is ready with the first stage, now go for the synthesis and transfer those code from RTL code to the gate level circuit, and that is the gate level module. Again at gate level again we have to simulate our circuit and verify doing is there any change during the transformation process. If there is any change, then we have to go back and correct our synthesis process, and if and go again to the gate level, and at this level again test bench is definitely required, that is the input function, and if that is okay, then we have to go to the next third step, that is placement and routing. Placement and routing is nothing, that is placement which module where we have to place. For example, in structural modeling we have, for example, we have 4 modules: OR gate, AND gate, then our half adder, full adder, and if those different components are there, which module, which component should be placed nearest, so that our communication should be having the minimum delay, minimum path. For example, if 2 modules are having maximum communication, we can place those components near to each other. If 2 modules are there, they are communicating very rare, then they may be placed some far away. So according to that placement or selection of components, then we have to go routing. Routing is nothing but that is the interconnects through the signals. And if our planning route placement and routing is correct, then our mean free path, that is minimum delay path, will be available, and if minimum delay path is available, then our system, our circuit, our design will be having the high speed, because that is having minimum interconnects and minimum time is required to transfer the signal from one component to the other. That is why that can be clarified with the help of the timing model and simulation. In the timing simulation, we have to verify how much time is consuming from one place, transferring the one signal from one component to the other. Then the final step will be the ASIC or FPGA implementation, that is ASIC is the application specific IC or field programmable gate array. These are the 2 types of the hardware ICs available. In application IC, they have their own advantage, that different IC can be designed according to their own application for dedicated application, but FPGA they are reconfigurable and multiple applications can be designed on the same FPGA, but application specific IC they will be dedicated one for the one application. So next in this hierarchy you can see we are started with the specification and step by step from coding to synthesis to placing and routement, and then we will go to the our ASIC and FPGA. Next I will show you how our FPGA design flow be followed. in the FPGA design flow, basically two main stages are there. One stage is synthesis that we discussed. We have to transfer RTL synthesis, we have to analyze our code analysis, and then in the implementation process, basically three parts are there. One is map, placement, route, and configure. In map, we are connecting the signals from different components. In placement and routing, as we discussed, we have to identify the place where a particular component suitable for connecting, so that there is we can reduce the delay and optimize our design. And then routing, that is the interconnects. Then configure, this is basically a transformation of our gate level design to a bit stream. That is, bit stream is nothing but a net list that contain that in the form of 0 or 1s, because our end product, that is FPGA or ASIC, that know only bit pattern, and that bit pattern we have to transfer to the FPGA for final design, and we can run our device. That is, in the start of our presentation, I have shown you basic VLSI design flow, and in the basic design flow we start with the basic specification and go up to the end product implementation, that is our running on FPGA kit or our fabrication. So in summary, we can say, I would like to summarize in this lecture. We will discuss, in the start we will discuss the basic VLSI design flow, then basic concepts of VHDL, then we take the discuss the combinational circuits and implemented with the help of VHDL coding, and then those VHDL codings simulated and then synthesized, and that synthesized process is ready for the implementation of FPGA with the different steps of placement and routing. In this way, we can design our combinational circuit model from specification to the end product. These are the references. Thank you very much. If you have any query, you can send me at the email, and we can discuss. Thank you very much for your patience, and I would like to give the special thanks to Dr. Bansal and Savina Bansal. Thank you very much.